Hello, welcome to another video where we are studying the motion of a charged particle that is inside a magnetic field that is constant. Remember that by now we have already made two other lessons talking about this topic. In the first one we found out what is the Hamiltonian associated to the particle, and then in the second lesson we found out what is the Hamilton-Jacobi equation associated to the system. Then we solved this equation and we found out that the solution to the Hamilton-Jacobi equation is this function s that I have here. So what we are going to do today is to find the equations of motion and then find the functions x and y as functions of the time. Okay, so this will tell us what is the motion of the particle. Okay, perfect. So we are going to start by remaining what is the relation between the coordinates and the function s. You know that we can express that pi is equal to the partial of s with respect to qi, right? So this means that we are going to get that px is equal to the partial of s with respect to x, py is equal to the partial of s with respect to y, then pz is equal to the partial of s with respect to z. Perfect. So we are going to say then that px is going to be, well, we need to take the derivative of this function s. So here we are going to get minus EB0y divided by 2, and then, well, is this element the one that depends on x, right? So we need to take the derivative. Okay, so to do this, well, we need to take the derivative of the integral, right? But looking that it is an integral of x, we can just say that the derivative of this is going to be, well, what is inside of the integral, right? So it will be 2mp1 minus p3 squared minus p2 minus eb0x squared. Perfect. So with this, we just found what is px. Okay, let me close this. And then, well, for py, it's going to be very simple. We can see easily that the derivative of s with respect to y is going to be minus eb0x divided by 2 and then plus p2. Okay, perfect. And then it's easy to see that pz is going to be equal to, well, p3, right? Okay, perfect. So these are the first three results that we get. So we have other equation for the generating function s. Recall that it is qi equals the partial of s with respect to pi. Okay, perfect. So what does this mean? Well, we are going to calculate three coordinates, q1, q2, and q3, and then, well, we need to take these corresponding derivatives. So q1 is going to be the partial of s with respect to p1, right? So that means that, well, we need to take the derivative of this element and this element over here. So for the first element is very easy. We will get just a minus t, right? And then here we are going to take the integral of the derivative, okay? I'm going to switch the order of the operators to take first the integral and then the derivative of what is inside here. And recall that is a derivative with respect to p1. Okay, so if we take the derivative in one step, we will get 1/2, and then this element over here, right, it is raised to the negative 1/2. And then times the derivative with respect to p1 of what is inside this expression, but that is 2m and then dx, right? So we will get that q1 is equal to minus t, plus we cancel these 2's, and then the integral of m dx divided by, well, this quantity that is raised to the 1/2, right? Perfect. So with this we have q1 already. Now let's calculate what is q2. Well, we need to take the partial of s with respect to p2. So if we look to our expression for s, we will see that we are going to get a y here, and then plus the integral of the derivative with respect to p2 of all these elements. So that is going to be 1/2 times, well, this expression, that is raised to the negative 1/2, and then we are going to multiply by the derivative with respect to p2 of what is inside here. So that is going to be -2, right? And then p2 minus eb0x. Okay, and then let me write the dx here because I no longer have space. Perfect, so with this we can see that q2 is equal to y, and then minus, we cancel these 2's, we have the integral here, it will be p2 minus eb0x, that multiplies dx, and then it is divided by this thing over here, that is raised to the 1/2. Okay, perfect. Yep, so that is q2. Let me remark this and this. They will be important later on. But for now, we are going to end by calculating q3. That is going to be the partial of s with respect to p3. And what is this? Well, with respect to p3, we will get a z here. And then again, we are going to take the derivative of this. So we will have a letter c here, and then it will be plus the integral of, well, again, it will be 1/2, and then times this minus 1/2, and then, well, the derivative with respect to p3, right? So that will be minus 2p3, and then dx. Okay, perfect. So with this we get that q3 is equal to z minus the integral of p3 dx divided by this quantity, and then raised to the 1/2. Perfect. So with this we have found q1, q2, and q3. Okay, perfect. So what we are going to do now is to establish what are P1, P2, and P3. Recall that this is to complete the definition of the canonical transformation corresponding to S. Remember that a canonical transformation is composed by some new functions, upper Q and upper P, and we need to express these functions in terms of the original coordinates. So with this, we already have Q1, Q2, and Q3, but we are still left with the P1, P2, and P3. But that is going to be easy because you can see that, well, P3 is already in terms of Pz, so we already have one equation. And from here, we can see that P2 is going to be Py plus Ev0x divided by 2. So let me write this over here. We have that P3 is equal to little pz, then P2 was Py plus Ev0x divided by 2, right? So now with this first equation, looking that we have what is P3 and what is P2, well, we can solve this equation for P1, okay? So let me rewrite this equation to do it in another space. Okay, so with this we are going to get that Px plus Ev0y divided by 2 squared, right? It will be 2m P1 minus P3 squared. But P3 squared is Pz squared, and then minus, and then we will have here P2, but P2 is this quantity over here. So, and if we subtract this, we will get, well, Py minus Ev0x divided by 2, right? And this is squared. Okay, so with this, we can solve for P1 to get that Px plus Ev0y divided by 2 squared plus Py minus Ev0x divided by 2 squared plus pz squared, all these multiplied by a factor of 1 divided by 2m is equal to P1, right? And you can easily identify that this expression that we have here is actually the Hamiltonian that we introduced in the previous lesson. If you look to that lesson, you can see how we deduced that the Hamiltonian of the charged particle in the uniform magnetic field is exactly this expression that we have here. So the thing here is that, well, we can establish that P1 is equal to the Hamiltonian. So with this, we have found what are the three equations that define the canonical transformation for P, for the upper P's, right? Okay, perfect. Okay, so what we are going to do now is to see how are we going to get the expressions x of t and y of t that are, well, the functions that are going to tell us what is the motion of the particle inside the magnetic field. So we are going to start by solving this integral. Looking that, well, if we are able to solve this, look that here is an x, right? So this x is going to tell us what is going to be that relation x of t. Looking that we have a t here, well, if we are able to solve this integral, then we will get that function x of t. So let me copy this expression in another position. Okay, perfect. So there's the integral. You should know that, well, it turns out that maybe the trigonometric substitution method is going to be useful in this case, right? I always solve these kind of integrals by drawing a rectangle like this, and we see that this has the structure of a Pythagorean theorem, where we can consider this as the hypotenuse, right? We call it C, and this can be maybe the adjacent leg. So we can let's establish the triangle in this way. And this will be the square root of 2mp1 minus p3 squared, right? Because it corresponds, this element, to the hypotenuse squared. And then we can define that this side of the triangle is going to be P2 minus EB0x. So if we name this angle as theta, well, we can say that cosine of theta is going to be P2 minus EB0x divided by the square root of 2mp1 minus minus p3 squared, right? And with this, we can see that P2 minus EB0x is equal to the square root of 2mp1 minus p3 squared cosine theta. If we are able to find this theta, then we are going to be able to find x, right? We just need to solve this equation for x and to see what happens. You will see later that, well, this is going to give us the function x of t that we are looking for. So let me, now we need to calculate the differential, this element of x, right? So if we do that, well, we are going to get here that minus EB0x, actually dx, right? It will be the square root of 2mp1 minus p3 squared. And then here we will have a minus sign of theta, of course, but with this minus it is going to be cancelled, and then it will be sine theta d theta, right? So with this, we can get that dx is equal to the square root of 2mp1 minus p3 squared sine theta d theta divided by EB0. Perfect. Okay, so we are going to construct again the integral. It will be q1 equals minus t plus the integral of m times dx. But dx is all this thing. So let me write this EB0 here, and then the square root of 2mp1 minus p3 squared sine theta d theta, and then all these divides, well, this thing that we have here. But how are we going to write this? Well, the first piece is going to remain the same, 2mp1 minus p3 squared and then minus, well, we have this, right? But it is equal to all this. So we are going to substitute that. So we will get that this multiplies the square root of 2mp1 minus p3 squared cosine theta, and this is squared, right? So it will be like this, and then this is all raised to the 1/2. Let me move this integral just for not to get confused with the quantity that we have above. Okay, perfect. So here comes the magic of this trigonometric substitution method. Here we are going to have minus t plus the integral of m divided by eb0 square root of 2mp1 minus p3 squared sine theta d theta, and then this is divided by, we will have here, look that this squared is going to cancel this square root, and then we will get a cosine squared, right? So we have a common factor of 2mp1 minus p3 squared. So this can be written as 2mp1 minus p3 squared that multiplies 1 minus cosine squared theta. You can very easily notice that, well, this thing is the same as what we have here. And this is all raised to the 1/2. Okay, perfect. So here is easy to see that this 1/2 is, well, the square root of this element, alright? So that means that we can cancel this element with this, and then we know that 1 minus cosine squared theta, well, it is equal to sine squared theta, but it is raised to the 1/2. So this is equivalent to a sine theta. So that means that we can cancel with this sine theta that we have here. So all this gets cancelled. And then we will get that q1 is equal to minus t plus m divided by eb0, and we only have the integral of the theta. Perfect. So we immediately see that this is equal to minus t plus m theta divided by eb0. So theta is going to be, well, first we will have a q1 plus t, right? And this multiplies eb0 divided by m. Perfect. So with this we have found an expression for theta. Look that it is a function of t. So when we plug this theta into the change of variable that we proposed, again we will have the x as a function of the time. So we need to take this expression and substitute the value of theta. So let me copy this here, and then, well, let me erase this theta over here. Let me switch it for q1 plus t eb0 divided by m, right? And this cosine is for all these elements. Perfect. And let me tell you something that is important. Here, I'm going to make a little spoiler. This element that we have here is going to represent a frequency. You know that when you have the variable t inside the cosine or the sine function, the element that multiplies that t always represents some kind of frequency, right? So this is telling us that we will have a periodic motion for the particle. So that's the first thing. The other thing is that, well, this kind of motion is going to be known as a cyclotron. Well, not this motion, I mean this physics example, the one that is for the charged particle inside the uniform magnetic field. Well, it turns out that it is known as a cyclotron. And this element, omega z, defined as eb0 divided by m, is known as the cyclotron frequency. Okay, perfect. So with this, well, we can solve this equation for x, and we will have that P2 divided by EB0 is equal to the square root of 2, actually minus the square root 2mP1 minus P3 squared divided by EB0 cosine of, well, this frequency omega z times q1 plus t, right? Equals 2x. And as you can see, the only variable in the left-hand side of the equation is the t. So this means that this is a function x of t. Perfect. And this is telling us what is the motion of the particle in the x direction. So this is the first important result by now. Yeah, so what we want to do now is to find out, well, the same thing but for the y, right? Okay, so to do that, we are going to remember this second integral for q2. We are going to copy and paste in a different page. Okay, there it is. So we need to solve this integral. In this case, it will be much easier than the other one because you can see that, well, if we make the substitution u equals 2mp1 minus p3 squared minus p2 minus eb0x squared. When we take the derivative, well, we are going to get what is here, right? So this integral becomes of the form du divided by 2eb0, and here we will have something like the square root of u, right? Yeah, this element appears because we are taking the derivative of what is inside here, that is minus eb0, and this 2 is from the minus 2 that goes down from the exponent here. So perfect. Well, we'll have here a very easy integral. We will be y minus it will be u to the 1/2 and then divided by 1/2, and then this multiplies 1 divided by 2 eb0. Perfect. So these 2 can cancel with this, and we will get that q2 is equal to y minus, well, the square root of u, right? But that is 2mp1 minus p3 squared minus p2 minus eb0x squared, and then this is divided by eb0. Okay, perfect. So what you can notice here is that we have an element p2 minus eb0x squared. So if you remember the solution that we found for the x, well, it is this one, right? But it came from this other expression that we have. So we need to raise this to the second power, and then that will cancel this square root and raise this cosine to the second power. So that means that the element that we have here can be substituted with this expression that we have here. So let me do that. Okay, so this is what we will get if we make this substitution. Now here is easy to see that this is equal to y minus 1 divided by eb0, and then the square root of 2mp1 minus p3 squared that multiplies 1 minus cosine squared of omega c q1 plus t, and this is, well, of course this will be sine squared of all this, and then if we take the square root, we will only get a sine. So we will get that this is y minus 1 divided by eb0, the square root of 2mp1 minus p3 squared sine of omega c q1 plus t, like this. Perfect. So with this we can just solve for y to get that y is equal to q2 plus 1 divided by eb0, square root of 2mp1 minus p3 squared, and then sine of omega c q1 plus t, like this. Perfect. So with this we have already a function y of t that is telling us, well, the motion of the particle in the y direction, of course. So I'm going to rewrite the expression for x and for y in this position now. Okay, perfect. So these are the two expressions that we found for x and y. Notice that I took the constant element to the right hand side of the equation just to be with the x of t and the y of t, right? So why did I do this? Well, this is because we are going to square both sides on these equations, right? For you to notice that what we are going to get is the equation of a circle, right? So this is going to be, well, for the first equation, we are going to get 2mp1 minus p3 squared divided by ev0. Let me make this, and this is a squared, and then cosine squared of, let's call this maybe as gamma, right? Just for not to write it all like this. And this is equal to x minus p2 divided by ev0 squared, right? And for the second equation, we will get 2mp1 minus p3 squared divided by e squared v0 squared, and then sine squared of gamma equals y minus q2 squared. What happens if we sum these two equations? Well, we are going to get that x minus p2 divided by ev0 squared plus y minus q2 squared, well, it's going to be equal to this quantity, which is a common factor, right? So it will be 2mp1 minus p3 squared divided by e squared v0 squared, and then cosine squared gamma plus sine squared gamma, which is of course equal to 1, right? So we can just take it out. So what I want you to notice here is that it turns out that the x-coordinate and the y-coordinate, well, they satisfy the equation of a circle, right? A circumference. So, and also we can say that, well, the center of this circumference is determined by these elements, right? Remember that the general equation for a circumference is x minus h squared plus y minus k squared equals to the radius squared, right? So this is telling us that the circumference is located on the center given by these coordinates here and here, right? So the center will be p2 divided by ev0, q2. And the radius will be, well, the square root of 2mp1 minus p3 squared, and then the square root of this, right? But that is going to be just ev0. So what is this telling us? Well, it turns out that, for example, if we have the coordinate system here, for the x here, the y here, and the z here, recall that we have a magnetic field in the direction of z. This is what we mentioned in the first lesson, right? That the magnetic field is constant and is, well, in the direction of positive z. So the thing here is that if we have the charged particle, let's say here, it will be moving in some way that the projection that it is going to make is going to be a circumference in the xy plane. Okay, let me draw this like this. So yeah, the particle is moving, right? It is making circles. This is what this equation is telling us, that during the motion of the particle, well, it is making circles in the projection on the xy plane. So it is moving all this and this. Yep, it's a periodic motion. And you may be wondering what happens in the motion of z. Well, recall that we found out that pz was equal to p3, right? So this is telling us that the linear momentum in the z direction is a constant. So that means that the velocity in the z direction is also a constant. It could be 0 or it could be different from 0. If it is different from 0, then we will have that the particle is making this motion, right? It is making circles on the xy plane, but it is moving up, right? Parallel to the z direction. Perfect. So, of course, if the motion in z, if the velocity in z is equal to 0, then this particle is only moving in a circle, like this. That's why, well, it is named as the cyclotron, right? Because it makes periodic cycles. Yeah, so the circumference that it is made, it is projected in the xy plane. So this is what actually this equation is telling us. And remember that what we found out for this projection circle is that, well, the center of the circle, let's say it is this point, it is located at P2 divided by EV0, Q2, and that the radius of the circle, well, it has a length of the square root of 2mp1 minus p3 squared divided by EV0. Okay, so that's the properties that we found for this circle for the motion of the particle. Okay, perfect. So, yep, I think this is a good moment to finish the lesson. This will be like the final important result. And the equations of motion given by these equations that we have here. Remember that in the y, it depends on a sine, and in the x coordinate, it depends on a cosine. Perfect, so I think I will finish the lesson here.